4. So we can make sure we can still know how to do these types of problems. Because you'll need to know how to do it in exactly 1 week. And 4 and then no wait, what time is that at? 7:30? 5 hours. So 1 week and 5 hours, you'll be down bad if you don't know how to do these problems. So let's make sure we know how to do this. So if 38.5 milliliters of lead-2 nitrate solution reacts completely with excess sodium iodide solution to yield 0.628 grams of precipitate, what is the molarity of the lead-2 ion in the original solution? How would we go about this problem?
The moles of lead or
Make
not lead,
like make a chemical equation.
All right, yeah, okay. So
So what type of chemical equation?
Balanced.
Yes.
the
Yeah.
lead-2 nitrate, NO3, is that aqueous or solid? Solid, I'm sorry.
It's aqueous. This is a precipitate reaction.
It's aqueous.
That is true, but we also know it's aqueous because nitrates are always solid, right? What about sodium iodide?
Also soluble.
Sodium's always soluble, right? And we're gonna get PbI2, which is what? Wait. So where should I start now?
I converted the grams of precipitate to moles.
Okay, so grams of
Grams
lead
of
to
lead-
iodide,
Yeah, lead to iodide. I converted that to moles.
and you did that using your molar mass, right?
Yeah.
Which we all know how to find of any compound given to us, which is 461.11
Yeah.
for 1 mole of PbI2. And then from here, where did you go?
I converted it to moles of the lead to nitrate.
Okay. So I'm gonna write it out on the exam. Yeah. So I'm writing it out so you can see like where the units are canceling out, but if you know that it's a 1-to-1 ratio in your head, and you just know that the moles of this is equal to the moles of lead-2 nitrate, then you don't have to do this little step up. I'll box it in there. Because all you're doing is adding or multiplying by 1, and that's just the same thing, right? So this step right here, I'm writing it out so that way no one gets confused. But again, if you know what that, it's a 1-to-1 ratio and the moles of PbI2 is obviously the mole of lead-2 nitrate, you don't even need to write that out. So I got 1.362 times 10 to the -3 moles of lead-2 nitrate. Is that what you got?
Yeah.
Okay. Now, someone else. What do I do once I have this portion? Okay, so you're saying it's asking for the molarity, right? So we need to use the molarity equation, obviously, which is molarity. I'll use red. Molarity is equal to moles over liters. We already found the moles, it's right here. So 1.362 times 10 to the -3 moles over, what's the liters here? 0.385. If you plug in your milliliters, you're gonna get that wrong just because the units are not correct. And I got 0.035. 4. Let's go with 3.6. And out of mold. Yeah.
If it was not a 1-to-1 ratio between the amount of lead in lead-2 nitrate or lead, let's just say it's like a
So
different
you're saying
compound.
if this wasn't a 1-to-1.
Or no, the next one, like
For
if you got
the,
mole for the ion,
like
like if there were more than
if there were more than
one
one
mole
mole
of lead.
Oh, I see. So you're saying if there was one, so if it was like this compound instead, so P 3PO4 2,
Yes.
then you would have to multiply it by 3. But yeah, so because there's only 1 mole, or in each of these, there's only 1 lead plus 2 ions, then therefore we know that it would have to, you don't have to do anything in this case. But yeah, if it was lead 2 phosphate, you would need to multiply this by 3. Okay. Perfect. Any questions? Okay, awesome. Now, the next question I wanted to do was, I think it goes straight to, no, there's one gas problem. Okay, 43. Why do real gases not behave ideally? What do we know about the ideal gas postulates or postulates of that?
There was 5 of them.
Name one, someone. So,
They would interact with each other.
so one of them is that they don't exert forces on each other, right? But we know real gases do exert forces on each other. The particles do exert forces on each other. So that's one reason. So let's just write one. Exert forces on each other. Okay. Next, we know the ideal, one of the postulates says that they're in constant random motion, which is true, generally true for all gases, right? They're usually in constant random motion, so I wouldn't put that one down. But what else do we know about the postulates? One of them is that each gas particle has a volume of 0. Is that true in real life? No, right? Because every atom, every molecule has some volume. So they contain some volume. Would be another one. Right. Any other the gas postulates being violated here?
But that they're not always at ideal conditions, because
Yeah.
the differing pressure and temperature can affect how they.
Oh.
You can say not always at ideal conditions.
And then would another one be that like there's attractive forces between different gas molecules?
Yeah, so that would be like number 1, where they exert forces on each other. Those forces can be attractive forces or repelling forces. What is another one that's being violated here?
So they exert forces on each other, they contain same volume, not always at ideal conditions. Why do gas not always at ideal? Well, there could be some elastic, or there could be some inelastic collisions between the 2 gas particles to where both particles stick together. But in ideal gases, we assume that they're elastic. So that means one particle will bounce off another particle.
Yeah, so what he's saying, one of the postulates is that any collisions in between molecules are elastic, but we know in real life that not all collisions are elastic, because what elastic collisions means is that momentum is conserved and kinetic energy is conserved. So inelastic, elastic is not always going to be true, because there's always energy being converted into things like heat, which we learned in class yesterday and today, right? So let's just say the last one would be inelastic collisions. So these are just things that are violating the gas postulates. All right, next thing, oh wait, it says under what conditions does a real gas behave most ideally?
High pressure,
High temperature, low pressure.
high temperature.
Yep, high temp, low pressure,
I still don't understand this.
really?
Yeah, I don't understand, because if you think about it, if it's a higher temperature, they're moving faster, so they're more likely to collide and have those collisions and attractive forces.
Yeah,
To me, that makes sense.
so, but if you're moving, okay, let me try to think of. So if you're moving really fast,
Yeah, I know the high five analogy, I know.
well, not that. I mean, yes, that, but like. It's much harder to interact with each other when you're moving that quick, because the amount of time that it takes if you're moving slow, you have a lot of time to make, have conversation with someone, but if you're moving fast past someone in a car, you try to say hi, they probably won't even hear you say hi fast, right? So there's not enough time for forces to be exerted on each other when they're moving super fast.
Wait, why do car crashes collisions transfer so much energy then when they're
Car
faster?
crashes are not gas particles. Yeah.
The car crashes are what's called inelastic collisions. So what happens is the two masses will sort of stick together. But what we're assuming, right, for ideal gases is that one particle will sort of bounce off the other particle. They won't stick together, so no forces are at play. That's why, like in a car crash, there's so much energy, whereas ideal gases, we assume there's no energy, though that's not always the case.
You think it would be better if we had elastic collisions on the road than inelastic?
Not really, because then it would be like a chain reaction. So like
Oh, yeah.
one car hits
To
another
go
car.
fly.
Like bumper cars.
Yeah.
No car.
Okay, so let's go to number 44. And Maria, if you don't understand it, like if it doesn't make sense to you, just know that these are the
Yeah, I know.
conditions, okay? Okay, number 44, I'm gonna give y'all 10 seconds to finish this. I'll say it might take less than 5.
I got this one in 1 second. You probably got it in like less than 1 second.
Yeah, it took me 1 second to think, wait, is that really it? It's
Exactly.
like, I took more time thinking, wait, there's no way that can be right,
Exactly.
thinking about it.
All right. So on 3, what is the answer? 1, 2, 3.
3. 0, I got 0.
You
0,
said 23.
Honey, I got 0.
I was trying to think how that was even possible.
Okay, so it says that the system's receiving a 425 joules of heat from the surroundings. That's going to be positive or negative. All right, so delta E equals plus 425. And then it's delivering 425 joules of work to its surroundings. Is that positive or negative? We all agree on that, right? Okay, so minus 425. 0.
Yeah.
Right? Hopefully we get one like that on the test, right?
Can you tell with that question?
You want me to go over it one more time?
So can you tell our one with that question?
Oh, okay.
So loud.
Yeah, I'll tell
That's
them. Probably,
all of us will know, the others won't.
for sure. Yeah, there's
It's
no way that they'll
changed
get
without
that.
bringing candy.
There's no candy?
There's no candy because no one reminded me last night.
No, because you forgot it.
I didn't. All right, do this problem 45. Okay,
Oh, we'll remind you.
I hope so.
Yeah.
You just don't forget.
I got
An
so many
alarm.
things. That's it. Yeah, 45. 45.
I had to move some stuff out of the way.
Is it that much work?
There's one thing you gotta do that might take up space,
You think I'll pick up steps?
but if you can fit it in, you can fit it in.
I've never used fresh paper on your tail. We'll have to next.
That's what I'm saying. You're gonna learn this today.
Yeah, these were these.
You're gonna learn this today. It's simple. It's the most easy equation ever. Delta E is equal to Q plus W. And adding and subtracting. Okay,
Bruh, why would you let us do that?
so get that out of the way. All right, so it says a system that releases 675 joules of thermal energy. We know if it's releasing, that's negative, right? It's what's it, thermal energy to the surroundings, and 530 calories of work done on the. So it's always important to know your units have to be like, right? So you can't add calories to joules because they're not the same units. So first we need to convert 530 calories to joules. And who remembers the conversion factor?
4.184.
Joules for every 1 calorie. And that should get you a number of about 2,217.52 equals. All right, so now we can add it, but what's the sign on the joules, on the word? Is it positive or negative? Okay, so positive. And then we already said that the releasing the 675 heat was negative, so we're gonna get delta E is equal to negative 675 plus 2,217.52 joules. And that gives me a number of positive 1,542.5 joules. What do y'all think?
So if it says releases, it's gonna be negative.
Yeah, so the system, in this case, it says the system releases 675 joules. So it's releasing, it's losing, right? So it's gonna be negative.
Practice for like 3 to 4. It's fine.
Sorry, I just put as many as I want. I look at the calculator.
But if we get a free response question.
What? We don't get free response.
If it's free response, it'll specify like enter your answer to this many significant conditions.
But they do that. Yeah, there
Yeah, but
are.
it didn't.
Some of us likely say do it to like 360. When in doubt, you can, if you don't know, like just look at your numbers first of all. And then if you don't know, still just do 360.
He had a PowerPoint and he didn't put that, and he's like, you guys should know by now, it's 366. He told us, yeah, it's 366.
Yeah.
That's our
I say-
lesson. Yeah, Dr.
I
Almond
say
said that.
360 is like a golden.
He
number.
forgot to put it, and then he's like, no, just do 366.
Okay,
That's what I
any
was-
questions on 45? Any questions on 45? Before we go on to the real thermochemistry. The fun stuff. This is actually the fun stuff, guys.
No, it's not.
Yes, it is.
It's satisfying.
Yeah, I can smell it. Really?
All right,
It's reverse.
so a 295 gram sample of aluminum engine part at an initial temperature of 13 degrees Celsius absorbed 75,000 joules. Yeah, 75 kilojoules of heat. And that it gives you the specific heat of aluminum. So, how many of y'all do not know how to approach this problem? Interesting. Hey, if you're gonna raise your hand, what does Aguilar say?
Wait, what does he say? High with pride. Raise your hand, high with pride.
There
We
we
don't know.
go. Okay, let's be honest, let's learn something here, okay? So. I'm seeing this problem and we are given a final temperature of a piece of metal and a initial temperature. So that's delta T. I think I see that and I'm like, okay, change in temperature, we have that. We're getting,
You're trying to find. It's just one thing.
oh my God, you're right. I'm sorry.
Yeah.
Never mind. Okay, so I see that we have a mass, right? We also have an initial temperature and we have Q. And then it gives us C. We have all the variables we need for a Q is equal to MC delta T equation, okay? So Q is equal to MC delta T. It says it absorbs 75,000 joules of heat. Is that gonna be plus or minus? All right, we all agree on that part, right? Everyone that raised their hand, we all agree on that,
Do we
right?
have to convert to joules?
Yes. Because the specific heat is in joules. See how this unit is in joules? So if you use 75, it'll be wrong. Okay, so 75,000 joules is equal to the mass time, or let me just plug that in, times 295 grams. And then we have the C, which is given to us as 0.9. And then the delta T, which is what we're solving. So if we just divide both sides by that, we would get it. Okay. We get some number, which I did not.
282. No, you can.
Because the initial temperature is Celsius.
Yeah.
282.49. So delta T is equal to 282.49. We all see where we've got that so far, right?
Can you explain that again? It's really hard to hear you on Zoom, because I think there's like voices interacting.
Okay, we'll make sure that no more loud talking goes on in the classroom that other than the people that are trying to explain things, unless you have a question, of course, okay? Please keep asking questions. Can you hear me better?
Yeah, it was just that because like overlapping noises will cause things like cut in and out.
Interesting, okay. Okay,
But
yes.
basically, did you just divide the heat, well, like the 295 times 0.9, divide that by the 7,000, whatever?
Yeah, so I did 75,000 and I'm trying to isolate delta T, so I'm dividing these two on both sides, so I get 75,000 over 295 times 0.9.
Okay, cool. That's what I got to. I was just making sure if that's the right steps. Okay.
You have to convert the temperature to Kelvin.
Or
no.
Yeah, it has
Isn't it the
bound
same?
Kelvin.
But isn't it the same?
Why is it in
unit?
Celsius?
No.
It's joules per Kelvin.
But like, it's like the same.
Yes, it's joules per gram degree Kelvin, but every like, if you increase your temperature in Kelvin by 1, you're increasing your temperature in degrees Celsius by 1.
Wait, so it's the same thing in this?
And since it's degrees, since it's change in something, it's like the change in, so a change of 282.49 degrees in Celsius is equal to a change of 282.49 degrees Kelvin. It's a change in something. And since it's not like going from Fahrenheit to Celsius where you have to like multiply by 9/5 and then plus 32, that's a weird conversion. It's really just adding a number, a constant, yeah.
Wait, but we're trying to find the final temperature. Would you have to convert the 13 degrees Celsius into Kelvin, or you just leave it like that? Would you have to convert that one down?
Probably, it shouldn't matter because the delta T is still the same thing. Let me see what I have.
If you use the word, couldn't you just add it at the end?
Yeah,
So don't.
no, you don't have to. If it's asking for it in Kelvin, yes, but it just says what is the final temperature, and since it gave it to us in 13 degrees Celsius, I'm gonna keep it in degrees Celsius.
But we shouldn't like subtract the 13 degrees from the delta T.
So right now, so delta T is the change in temperature, which is equal to the final temperature minus the initial temperature.
So, wait, that's degrees Celsius?
This-
282.49.
Yes,
That's because it's the same thing as Kelvin.
because it's a change in temperature. It's not saying the temperature is this. It's a change in.
So you're gonna subtract 13 from that?
Yeah. Okay, so if you have let's say you have a final temperature at, let's do some easy numbers. A final temperature at 20 degrees Celsius and a final temperature or initial temperature at 10 degrees Celsius, okay? The change in temperature is what? In this case? 10, right? Now, if you convert it to Kelvin, it's gonna be 273 plus 10, which is 285 or 283. And then 273 plus 20, which is 293.
I know, I
The
understand that.
change is
part.
still 10.
I understand that.
Okay,
part,
so
I
what-
promise. But the thing is, if you subtract, like, for example, if I converted 13 to Kelvin, right? I'm gonna be subtracting 286. But if you just subtract 13, you're gonna get a way higher final temperature.
But you don't need to
I mean,
convert it
add
to
your
Kelvin in the
final.
first place.
It's the same one. if you use Kelvin.
No, if you converted 13 degrees the initial temperature to Kelvin, it'd be a completely different answer than if
Well,
you.
then you can convert it back to Celsius.
By
Like,
subtracting.
yeah, because.
Yeah, like you're gonna get a different, okay. Let me find the final temperature first, okay? And then I'll show you that the temperature in Kelvin is obviously different because if it's in degrees Celsius, you have to add 273 to get to Kelvin. You should still get the same answer if you were to convert it back to one another. Okay. Okay, let me see. So
Kelvin and Celsius are on the same scale, right?
they're not, well, All you're doing is just adding 273. It's a constant. So you would add 273 to your initial and add it to your final.
Yeah, so the difference would be the same either way.
What did you get for your answer?
Not hard thing,
What did you get for your answer?
I converted it to Celsius like we had done in other problems. I didn't think of the fact that I would need to do that. So I got like 22.34 degrees Celsius. And then I also listed in Kelvin where I got 295.4
Okay, so I'm adding the original 13 degrees. And I'm getting a number of 295.49.
So my answer in Kelvin is correct, but the answer in Celsius is not.
What did you get from Kelvin?
295.49.
I think it's degrees Celsius.
Yeah,
See what I mean?
like I just assigned like, I got the right number. just no three.
So 295. Oh, that looks bad. 295.49 degrees Celsius is what I get when I just do it the way, without changing any of the things to Kelvin. And like I said, the units for specific heat are, they can be joules per gram degrees Celsius or joules per gram degree Kelvin. It's all the same thing. Because a change in temperature of 1 degree Kelvin is equal to a change in temperature of 1 degree Celsius.
Like on the test, will he give you the specific heat?
Yeah. So everything you're going to be given the specific heat for anything other than water. Water you need to memorize. Okay.
Yeah,
So how'd you get to 295?
So we did 75,000 divided by 295 and then divided by 0.9, right? And that gives me the delta T is equal to 282.49, right? And then we know that delta T is equal to the final temperature, which is what we're looking for, minus the initial temperature. So I added the initial temperature to both sides, so plus 13 here, plus 13 here, and that gives me 295.4.
I have a quick question. So the specific heat is like given in Kelvin. So do we not have to convert it to the delta T in Kelvin?
So like I said, that if it's given to you in Kelvin, it's the same thing as if it was given to you in Celsius. Because because the specific heat of water is 4.184. Okay, it's already here on the left side. It's 4.184 joules per gram degree Celsius, but it's also 4.184 joules per gram degree Kelvin. It's the same exact thing.
Oh, okay. So because it's the same, they're basically the same when you use a specific heat.
It's just changing the temperature. The whole definition of specific heat is the amount of energy required to change the temperature of a substance, of 1 gram of substance by 1 degree Celsius or 1 degree Kelvin. So it's the same for either. Okay.
Yeah, is there a reason why it's the same despite like Kelvin?
It's like it's
being-
changing because going from Celsius to Kelvin, all you're doing is adding a 273. It's just a constant. So changing the amount, changing from 1 degree Celsius to 2 degrees Celsius is the same thing as changing from 273 Kelvin to 274 Kelvin.
Okay,
It's just a 1 degree difference.
okay, I kind of get it, I think.
Okay. So, any questions? I know some people are probably confused. Do you know that you're able to interchange the Kelvin for Celsius or Celsius for
I
Kelvin?
see it now. It's just
I understand. I need to-
conceptualizing it.
Okay,
This is a dumb question, but the units for delta H, is it joules or?
what was that?
delta H is usually kilojoules.
So how's the?
Yeah,
All right, so a 27.7 gram sample, wait, we're doing 48. This is kind of a similar problem. I'll give y'all, for simplicity, I'm gonna cross out Kelvin again and put degrees Celsius, just so we don't run into the same problem again.
just know like if you get that on the test, like degrees Kelvin is the same thing as degrees Celsius.
Yeah, and if it had said, what is the, like, going back to the previous problem, if it said, what is the answer in degree in Kelvin, you would just add 273 to this and get your answer, okay? So go ahead and let's solve that out. Anyone still unsure how to do this one? What about the people that originally raised their hands? Are y'all, okay, I'll give y'all some time to work on this one. So that way we can see how much we got.
I have that was from my notes already. I think being used in another room, so that's nice now.
By doing what?
I think whenever I originally solved this, I converted both to Kelvin.
Yeah.
It was weird, but I just resolved it like I should have, and I got thing Celsius. I don't know how.
That's what I'm saying. I don't think it matters how you do it. Because if you get an answer in Kelvin and you just subtract my 273, you'll get the same answer in Celsius. Well, you'll get. I'm not.
It's because like when you're doing these problems, it's talking about temperature in general. So like it doesn't matter
Yeah,
like
I
what
think-
scale.
See how I got this one right, but the other one wrong, even though I did the same thing.
What did you do on the?
Okay, so the first one, like 47, I converted 1 to Celsius from Kelvin. This one I just converted the other one to Kelvin and then converted it to Celsius. Weird.
Yeah.
I resolved it. I mean, it's now.
Okay. Okay, how much more time do you? Maria, you need more?
No,
Are you mad that I forgot the candy?
I didn't even know you were bringing candy.
Oh, good. Mad that you forgot the candy.
Yeah, I'm personally kind of upset.
Personally.
Yeah, I do that real personally.
Hey, your stars tutors won't ever bring you candy, so.
I don't have one up on you fraud. I feel like that's almost more stars.
Stars are in the sky.
No, it is.
Another.
Okay, I'm gonna go ahead and get started on this problem. So it says a 27.7 gram. What is,
You meant to say of the
yeah,
radiator.
okay, that makes sense. Of the radiator coolant ethylene glycol releases 688 joules of heat. What is the initial temperature of the sample? If the final temperature is 32.5 degrees Celsius. So it's asking what is the initial temperature in this case? Where should we start? Okay, so you're saying we have everything we need. We have the specific heat of ethylene right here.
Everything's.
We have mass, we have the heat. So we have 3 out of 4 variables, right? So Q is equal to MC delta T. It's absorbing, it's releasing the heat. So that's going to be what, positive or negative?
But I'm confused there because if that's negative. And it's saying that it's releasing heat, meaning the initial temperature is gonna be greater than the final temperature.
No, not necessarily.
If it's releasing heat,
It doesn't, we're solving for the initial temperature.
Yeah, we're solving for the initial.
but doesn't, if you have more heat at the beginning. Wait,
The
if
initial
you,
temperature is negative.
okay,
Is it
never
not
mind, I'm just
negative?
gonna watch,
Yeah,
I'm gonna watch how
it's
you'll solve
negative.
it. And then I wanna see.
No, you
Wait,
just
you
put
got
it
a
in
negative?
Yeah,
Right?
The negative number.
yeah, I've heard the
Wait,
negative.
wait,
Oh my God.
See, that's what I'm
I got a negative number
confused.
for initial temperature, that makes no sense.
Shouldn't it be great, shouldn't the initial temperature be greater than the final temperature because it's releasing
Wait, no, the
heat?
change.
Wait, isn't it?
So it should be,
It is.
The
it
change
is, I'm just gonna see how y'all do it because I,
Okay. Okay, so
Okay, it's.
are you okay?
I'm going insane.
Relax. Take a breath. Okay. So we have, it's releasing heat.
Initial temperature. You forgot your negative.
Yeah. So now we have to plug, let's just go and solve for the T final. So we can say that Q is equal to MC times the final temperature minus the initial temperature, right? I'm just gonna solve it this way rather than the previous time where we kind of solve for delta T and we can plug in everything we have. All right, so it'll be, if you isolate that, it'll be Q over MC is equal to T final minus T initial. All right? So now I'm gonna do another math thing. I'm gonna add T initial to both sides, and then I'm gonna add or subtract Q over MC to both sides, okay? So you're gonna end up with something like T I is equal to TF minus Q over MC. Okay. Does that make sense? Okay. So let's go ahead and plug in. I'm gonna go bring this down to the next page. So Ti is equal to, the final temperature was 32.5. And the, what was it, minus Q. 688. 688. Trying to think, I'm looking at my key right here. And I didn't put the negative sign inside.
You gotta add it to the final temperature.
Yeah.
This is a really tricky question.
The delta T.
Yeah, but I think he meant that like.
Shouldn't Q be negative? Shouldn't Q be negative because it's being released?
Yeah, it should.
Yeah.
So the Q negative.
So
then-
negative and negative. cancel out.
Okay, I see. So it's gonna be 27.7 grams. And we're starting to invade this number 17.
Because it releases joules.
And then it's gonna be the 2.42 joules per gram degrees Celsius. And when we figure that out, what is the temperature? 42.8.
Same thing.
42.
So that originally.
We're just gonna say 42.8. That makes sense.
I got that, yeah.
don't know how I converted
You added it.
But I did.
I got 22 too, that's how I got it.
I have a quick question.
Yeah.
So when I originally did it, I did like the top way where like I had this delta T. And so when I ended up doing everything, I got the same answer but negative. I think I know what I did wrong, but would separating it into its separate components be the way to do this problem?
I think it makes a little bit more sense. when
Yeah,
I
it
do
does.
This way, just because you have all the variables there and you're not solving. I think you can algebraically solve for TI before you plug in numbers like I did. So I don't know how y'all like to, oh my God, what's going on? I don't know how y'all like to do it, but I like to solve for the variable first
Yeah.
and then plug in numbers, because that's the only way you should be doing it, right? Because with
You keep doing it different ways though.
well, because some people do it other ways. Who prefers to plug in numbers?
No.
See, some
The wrong way.
Depends.
I feel like you take calculus, why are you doing it that way?
Yeah, and then I just.
No, I took calculus in high school.
Yeah, and I started
So it's
doing
even
it.
lower.
His way, that's.
Not good.
I mean, I messed it up.
All right, next question I wanted to do was. If you want to do?
Oh,
Yeah.
So this one is I'm gonna be honest, I hate these problems. I hate these problems so much.
All right, I'm gonna call this one a behemoth, so I'll give you all about 7-8 minutes. to this. That's fair.
Read it. Wait, you wrote it all down?
Compare,
How did you?
like you said, and to do the questions that you know, like you said.
Why didn't you just print it?
Yeah, for real. Why don't you just buy an iPad?
Pretty sure I did it.
So the volume. I didn't. So, no, but you know what you should have done? You should have added like the total. Yeah, I have to say.
There was this one guy.
Trees.
Gosh, there's one guy, he didn't do front and back, so he couldn't like. All
It's
the
just a matter of
26
the word
pages.
column. Just
Well, no, actually, it was like 40 pages.
It's really-
I gave him my answer key as well, so it was like quite a bit. Yeah.
That's
like
the
this
biggest
problem
thing, solve for everything for delta T and then you'll
Like I
kind
saw.
of subtract it the wrong.
Yeah, cause like, don't use the Q equal like something.
Figure out where you want to put your negative signs.
Yeah, I did that, it's
I
not.
haven't even read it. Hold on, so this one.
I
Really?
just use the density equation to get the math.
Cause I forgot the math. I messed up somewhere.
That's pretty long, dude. That's okay. Hey, what did- what answer did we-
That's the same as the one.
Answer. Okay, you're looking for delta H of the reaction. So did you divide by moles?
The heck is the delta H?
Oh, yeah, you
I don't
know
know.
that's.
Do you, wait, do you find out that part?
Yeah.
Delta H is equal to, no, that's way off.
Yeah, we both got it wrong.
Delta H is equal to Q over the amount of moles.
Oh, okay.
Yeah, because the units right are like kilojoules per mole, since your heat's in kilojoules, and then you do it
I
just
don't
per mole.
You told us that equation yesterday.
Wait, so if you're solving for Q, can you just,
Their ribs are so good.
instead of putting in your mass, can you just put in your moles?
Yeah, you were.
The
because
brisket's
it
not my
was the
favorite.
second half of the slide,
Then you're
that
not-
Dr. Armand did not tell us.
And this place.
That's right.
Yeah, dude, the brisket.
You didn't tell us what.
Salt looks better.
What was this equation yesterday?
I think I got it, but I'm not sure.
How much math?
Why did you use? It is, like, why can't you? do it and have out-
Did that work?
And you have enough. What was the answer again?
42.8.
Figure out how much heat is lost by one.
Alright.
Yeah.
Times three
Over
colors.
mix. Into a solution. What the, no.
You just divide Q and then divide by moles.
Find the Q, exactly.
What did I do wrong?
Did you find the limiting reactant?
Yeah,
Um,
when you find mass, you just add the limits of like all the reactants.
I feel like there's a lot of extra information here.
I don't like
I don't know.
thermochemistry. You don't like thermochemistry?
No.
Stoichemistry and thermochemistry.
I mean, you guys will like the next set of chapters. It's not this difficult.
Oh.
What's
What is
what's the
it?
next code chapters?
It's like quantum physics.
Yeah, you gotta learn about
Oh,
quantum
that's
numbers,
fine.
like ionization energies, like periodic.
It's easy stuff. It's pure memorization. This is all
I'm better at math than memorization. Which makes sense.
I'm switching to comp sci after this semester.
What are you in right now?
So just because I don't know how much more progress y'all are making, because it seems like people are kind of stopped working or something.
Yeah.
I think either you got stuck or something, so I don't want to waste any more time, so let's go, you can go ahead and start.
All right, let's go ahead and get y'all unstuck if y'all are stuck. So, first of all, what y'all do is the first step.
I wrote a balance
equation.
I would also write a balanced equation, so let's write out a balanced equation. So we have silver nitrate, AgNO3. Is that aqueous or solid?
Aqueous.
Aqueous. Why is it aqueous?
Nitrates are always soluble.
Okay. And then we have our NaCl. That obviously is aqueous,
Yeah.
because it's a strong electrolyte.
And it's also, it's all, because
Exactly.
it's also always.
And then what are your products?
Yeah. Sorry.
Ag, silver chloride and sodium nitrate.
Silver chloride and sodium nitrate. Yep, those are exactly the
It's
products.
already balanced, yeah.
Yep, and then which ones are, what are your physical states? For AgCl, is it solid, aqueous? It is a solid, because silver is the exception to chlorine. What about sodium nitrate?
Nitrates are always soluble.
They're all solid. That's aqueous. All right, so what would be the next step?
Yeah, use the polarity to find the mole.
All right, so yeah, that's exactly it. So step one, we're gonna say find limiting. So if we solve this out, right, we'll get, and then we know, right, that our molarity is equal to moles over liters. So our moles, right, will be equal to molarity times liters. So we'll do that for each of these. So if we do 0.2 times 20 over 1,000, so it'll be 0.02 times 0.2, which will equal 4 times 10 to the negative 3 moles of AgNO3. And how I got those, that number right is I multiplied out these two numbers together, and then I came up with that. And then the next thing I do is I'll do the same thing again for the next set of numbers. So 30 and point. So same exact formula. So I'll do 0.1 times 0.03, and then I'll get 3 times 10 to the negative 3 moles of NaCl. So now we have both the moles of our reactants, right? So I'm just gonna go ahead, this right here, copy. All right. So now we have the moles here. So what is our next step?
Find what one's limiting.
What was limiting exactly? And
It's a 1-to-1 ratio, so this would be the.
exactly, it's 1-to-1 ratio. So
We'll say it just equal to-
well, you said it's the silver
Wait,
nitrate.
yeah.
No, it's not.
Getting what is exponent to the sodium chloride,
Exactly, since
because it's the.
as the person in the front has said, it is a 1-to-1 ratio, in fact. So it is 3 times 10 to the negative 3 moles of
Yeah.
NaCl, or sorry, not NaCl, AgCl. And then also the same right here, so you'll get 4 times 10 to the minus 3 moles of AgL. So not AgL, 3 AgCl. So as you stated, this is in fact our limiting reagent. So we are now done with that. Now what we'll do is we'll keep this number aside and then move on to the second step. What do you all think is the second step?
I found the
Finding
mass
Q.
of
Solve the Q.
Yeah, I would also solve for Q. So solve for Q. So what is our formula for Q? Yeah, exactly. Q equals MC delta T. So are we given enough information right here to do the Q for our reaction mixture?
Yes.
Yes, you have the moles of,
Yeah. You have the moles.
you have the moles of AgCl, you can convert that to grams of
But
AgCl.
we don't specifically.
Specific heat, because specific heat
It
is
says
the
it's
same as
water.
water.
What's a simpler way?
We could take Q and turn it into delta H.
I mean, we can't really do that.
Delta H is Q over N, so Q is not equal.
And M is just we know our molar mass. So we can divide both sides by moles, and instead of plugging in our mass, we just plug in our molar mass. And that'll solve for delta H.
But it's moles of like product.
Yeah, we have our moles of product.
You said molar mass.
We're dividing by moles either way.
Right, yeah. So point being, so right, I was pulling y'all's leg. We do have enough information to solve for the reaction mixture Q. So what we're gonna do, right, we need the mass. So we're gonna use the molar mass. So 4 times 10 to the minus 3. Wait, is this nope, wrong number. 3 times 10 to the minus 3. Because that's how much product we make. 3 times 10 to the minus 3 moles of AgCl. And then we'll use our molar mass right here to convert this to grams. And the molar mass of silver chloride is approximately a number that we will solve for.
It's like 107.
107 was like 35.
Yeah, 35.45.
So.
142.45 grams, or, yeah, oops, put down the wrong side. So 142.45 grams of AgCl are in 1 mole. So if we solve this out, we should get a number of approximately,
I'm not sure how you're planning on getting.
it'll get there.
Wait, what were you saying? The specific,
I was saying you're gonna cancel out your moles to solve for delta H anyway, see,
but you said the specific heat of what is the same as water?
Good question.
The equation, or the question says that.
It says the specific heat of the solution, not the specific heat of silver chloride.
That would make me so confused. Why we do so?
What were you saying? You can use the specific heat?
I didn't say anything about specific heat.
What was the specific heat?
Louis says something.
Could be me, I don't know.
I lost.
So we found the limiting reactor, right? Okay. So yeah, we want to solve for Q. And it says that the heat, we know that the heat lost by the reaction is the heat gained by the water. And it says we can use the heat, the specific heat of the water is the same, even though there's stuff dissolved. Okay, that's basically what this part is saying. Assume that the specific heat capacity of the solution is the same as water, okay? So it's saying that even though it's a solution, it has solutes in it, you can still assume that the specific heat of that is 4.184.
So you can take that for AgCl?
No,
No, wait,
it's of the water. We're saying that the solution is gaining the heat from the reaction.
what's the solution in this case? I'm confused,
It's a-
sorry.
The solution is the combination of NaNO3, all these ions in solution, which is a water-based solution, aqueous, okay? And that solution is what's absorbing the heat from the reaction, right? Yes,
You lost me there.
okay, so the reaction is releasing heat, right?
Yes.
What's gaining the heat,
The solution.
right?
Yeah.
That's, so, let me go ahead and say the heat lost by the reaction is equal to the heat gained by the water. We agree on that, right? Or the water in this case is in fact a solution, but we're just assuming that it's water, okay? Because that's what this is saying, is that you can just treat it like it's just pure water, okay? Even though there's some ions in there, okay? So from there, what we say is if we're looking for the Q of reaction, we just multiply by both sides by -1 to solve for Q of reaction, right? So we can say Q reaction is equal to -Q H2O. I just multiply both sides by -1, all right? I just moved the negative from the left side to the right side to solve for Q of reaction, all right? So now what we can say, jump down here, and we'll do Q reaction is equal to the Q of H2O. But we have a negative here now, right? And we have 50 grams of water, right? Because we know the density of water is 1 gram per milliliter. And we have 20 milliliters in this sample, and we have 30 in this sample. So it's 50 total, right? Right? We agree on that? So that's how much water, the mass of water. 50 grams of water. And it says we can use the specific heat for the water to be 4.184. Okay? So 4.184 joules per gram Celsius. Okay, so anyone have any questions so far? Okay. So if you have a question, yeah, go ahead.
So where does the 50 grams come from?
Yeah, so because we know that the density of water is 1 gram per milliliter, right? We learned that earlier this year.
Right.
We can say that the 20 milliliters plus 30 milliliters is equal to 50 milliliters. And that's why it says down, and it kind of hints at it right here by saying the density and specific heat capacity of the solution are the same as water.
Okay, that makes
So
sense.
the only way you can solve this problem is if you take this hint and say, I can find the mass of the water by using its density, and which we know is 1 gram per milliliter, okay?
Yeah,
Does
that makes sense.
that make sense with everyone in here? Because I see a lot of blank faces. I don't want y'all to walk out of this session not knowing how to do this problem. So do you want me to start from the beginning and explain? Okay, so we started off with a balanced chemical equation, right? And we're given information about both reactants, right? Which tells us we have to find what? Limiting reactant. We're all good there, right?
Yeah.
So we found the limiting reactant. This is how many moles of silver chloride we would expect to be produced. I'm sorry.
Okay.
Okay, so this So now that we found the limiting reactant, I'm gonna cross this one out because it doesn't matter, right? So from there, we found the moles of that. I'm gonna leave that there for later. I'm gonna come back to that in a little bit. It's gonna be useful in a little bit. So now we need to solve for the heat that was lost by this reaction. And we know that the heat lost by the reaction is the heat gained by the water, right? We all agree on that. That's the conservation of energy, right? Whatever's lost by one thing has to be gained by another thing. Does that make sense? Okay. So now I just swap the negative sign over to this side so that way I can solve for cube reaction. And now I need to explain why I'm solving for cube reaction. And it's because the enthalpy equation is delta H is equal to the cube reaction over the amount of moles that was involved in that reaction, okay? So in order to solve for delta H, I need to find the cube reaction, which is why I solved for cube reaction here, okay? So from here, I'm plugging in my MCAT equation for the water, okay? So we know this is equal to, so we say cube reaction is equal to negative Q of H2O, which is equal to a minus sign times the mass of H2O times the specific heat of water times the change in temperature of the water. Are we good so far? That makes sense? What about people on Zoom? That makes
Yes.
sense? Okay,
Wait, real quick. Why did you put the negative sign for onto water? Like it was on the reaction side, you just moved it over?
yeah, so it was like this, right? At first. Correct?
Yes.
So, but I need to solve for cube reaction. I don't want to have negative cube reaction. I want to have cube reaction. So I'm switching the negative sign over so that way I can solve for cube reaction, which I will then plug into here later.
Okay, so basically because they are conserving energy, the negative doesn't really matter where it goes.
Exactly. And it's
Okay.
because in here, I have to figure out what the cube reaction is. And when you move this negative over, it's going to give you a negative number for your final answer, which makes sense, right? Because if the solution, if the water is gaining energy, that means the reaction is losing energy,
Right.
right? So
And vice versa.
yeah, exactly.
Okay, perfect.
Okay, so to go from here, the change in temperature of the solution or the mixture was 25.65 minus 24.72, which gives me 0.93 degrees Celsius. Are we good on that part? It's just finding the delta T, right? So I'm gonna find cube reaction and I'm gonna multiply this number out and I'm gonna get negative 194.556 joules for our cube reaction. And does that number make sense? Does it make sense that it's negative at least?
Yes.
And why does that make sense?
Lost energy.
It's losing energy, right? And the water is gaining energy, which means that something has to be losing energy. And that's the reaction. Yeah.
Like totally random, but like just to make sure Q is the change in energy or change in heat.
So Q is just the heat associated. So in this case, the Q of the reaction is how much heat was lost by the reaction. Okay. And it's not the change in anything. Remember, it's a path function. It's not the change. It doesn't concern about the final or the initial state. It's just in this one reaction, this is how much heat was lost by the reaction. Does that make sense? Okay. So this part is going to be plugged into here. So we're going to get delta H is equal to Q of reaction over N. And had I not moved the negative over, we would have ended up with a positive value here, which wouldn't make sense, right? Because it's not, the negative would still be right here. And we're solving for Q of reaction, not negative Q of reaction, okay? So that way we can plug it into here. Yeah.
Do you always consider the Q of reaction as minus before you negative?
It depends on the scenario. So sometimes some reactions are endothermic, where it's going to decrease the temperature of the water and not increase it. So then in that case, the Q of the reaction is positive because it's taking in heat.
So if this was like, if the temperature went down in this situation, then would you have started with Q of reaction of equal to negative Q of water?
Exactly, yes.
Wouldn't that give you the same answer? Because you still just move the negative to the other side.
I guess, but well, it would have to be a totally different reaction.
They
Oh,
usually
the
tell you,
temperature change would be negative then, right? So then,
To compensate for it, yeah.
okay,
it'll usually
That
tell you in
makes
the
sense.
questions, like whether it'll like absorb the heat, and then you can figure out your Qs and negative Qs from that.
Okay, so. Yeah, right there. Okay, perfect. All right, so now we're gonna plug everything in. You're welcome. Have a good one. So negative, the Q reaction is negative 194.556. Oh, you messed up. I forgot one thing. We need to convert this to kilojoules because enthalpy is always going to be in kilojoules per mole. So this is actually going to be, if you divide by 1,000, you would get 0.194556 kilojoules. And then you have to divide it by the moles, but we're dividing by the moles of the limiting reactant because that's actually how much is produced, right? Or that theoretical. And it's asking, it says it wants us to find the delta H in kilojoules per mole of AgCl. So that's how I know I'm dividing by the moles of AgCl and not just the moles of anything else, okay? So that tells us in the problem. And we're gonna do that and it's gonna come out to be, so 3 times 10 to the minus 3 moles. And we're gonna get an answer of negative 64.9 kilojoules per mole of AgCl, which is our delta H.
Quick question.
Give me 1 second. You're fine. Okay. Okay. That was a bad one. Okay. Okay. We're done.
Can we convert to kilojoules after we get our answer? We can, right? Doesn't matter.
You probably could, yeah. I think you could. If you want to, you can check it right now if you want. So it would be 190 or negative 194.556 divided by 3 times 10 to the minus 3. And that's joules. Yeah, you would get the same answer. But I just simplified it earlier, but yeah.
So basically, anytime it's like coffee cup calorimetry, so we would use the equation like negative Q reaction equals Q water because the transfer heat.
Yeah, exactly. So that's the base equation you need to know is where heat's being transferred from one thing to another. But then you need to be able to apply the MC delta T equation to solve for either the heat of water. And a lot of the times, since we always know the specific heat of water, you can always solve for the heat gained or lost by the water, which will help you solve for the Q reaction, right? But yeah, what's up, Bobby?
so when it says the mixture increased 25.65, is that referring to the water's temperature or the temperature?
Yeah, the mixture increased. So
So the water is absorbing heat, but then the ions itself, like the
no,
reaction.
remember if you were to write out a net ionic equation, your reaction would be Ag plus Cl minus gives you AgCl. So that's actually the thing that's reacting, and that reaction actually has to take energy or releases energy into the surrounding environment because you're forming bonds.
So, but the temperature change is only the water, it's not the ion.
No.
So when it says the mixture increases, it's just saying like the water's temperature is increasing?
Yeah, and it tells you the initial and then the final, yes.
Okay, so that just means that the ions are, or like the reaction is exothermic?
The reaction between silver plus and Cl minus is exothermic, yes.
Okay.
I have a question.
Yes.
And so for delta H, it will always be in kilojoules, you said.
Yeah, it's always, the units for delta H are always going to be in kilojoules per mole. So if you forgot that your answer, if you had not converted it to kilojoules like I did, and you were going to wait till the end, but you forgot, and you put it in joules per mole, you would get the wrong answer if there was a pre-response question in the I-clicker. Okay. So who wants me to talk through this problem one more time from the beginning to the end? Anyone want? Okay, we got one person. If you're gonna, if I see, are you okay? You look like you want me to, but you don't want to say you want me to. I can hear you. What? Yeah, it's a lot. So I'm gonna go through it one more time. Yeah, you have a question?
Yeah, so, why couldn't we have, once we got in the moles, just found the grams of AgCl? Is it because we had,
Oh, you don't have a specific heat of AgCl.
so that's why we're using water, 'cause we don't have a specific heat. of AgCl.
Exactly, because we have to recognize,
Oh,
you have to recognize that the heat lost by this reaction is equal to the heat gained by the water. And that's our way to figure out what the heat of the reaction was.
yeah. Oh, okay, because the first time I used like the grams of AgCl, so I got a completely different answer. This makes sense.
I see, yeah, so this is, again, this is the key equation, we have to realize that, okay, I'm not given any specific heat of AgCl, but. So I have to find the Q reaction indirectly almost, by finding out how much heat is gained by the water, which tells me automatically how much heat was lost by the reaction.
Yeah.
So that's, you have to recognize that in these problems, this little equation right here. So I'm gonna start from the top and explain this whole thing one more time, okay? I'm gonna interact with y'all while we do, okay? So what's the first thing we did?
Wrote out the equation.
Everyone start interacting here, okay? I want to make sure everyone. So yes, we wrote out a balanced chemical equation, right? Second thing, everyone.
Limiting reactant.
Thank you very much on Zoom. Yeah, we found the limiting reactant, right? Why did we know, how did we know we were supposed to find the limiting reactant?
It gave us
It gives us two things.
It gives us information about both reactants, right? That's how I know, and that's how we all know that we're supposed to find the limiting reactant. Next thing, after finding the limiting reactant, we need to find the heat associated with this reaction, right? So we did that by indirectly finding the heat gained by the water right here. And we found the heat that was, we added the negative side to the other side. So we solved for Q reaction, right? And that tells us how much heat was lost by the reaction. But this is, we use the heat gained by the water indirectly to find how much heat was lost by the reaction, right? That makes sense. I have a prettier one I could send you. This, you can come take a picture of this one over here. It's actually kind of nice. It's all color coded and everything. Okay, maybe, yeah, okay.
This guy really is in my handwriting.
It could be better, Rich. It could be better. But it's the doctor handwriting. He's gonna be a doctor.
Exactly.
Okay, so we're good on this part, right? But, and we also know why we're solving for the Q of reaction. And it all goes back to this equation up here. In order to find the delta H of reaction, we have to have the Q of the reaction. And we have to divide it by the moles. So here we found the moles. And this is, so this is the base equation, the very basic principle of why I'm solving for Q of reaction, okay? Is this equation right here. So if you don't remember what to do, try to start here and then say, okay, I need moles. I can find moles by finding the limiting reactant. I need Q of reaction. And that's when we said, okay, we're gonna find it indirectly by finding how much water, how much heat was gained by water. And then we just plugged it back in, everything back into this equation. Does that make sense? All right, there's a similar problem as like number 49. We can do that too.
Are we gonna do that right now or next time?
We can do it now if y'all don't have anything to
And
do.
total volume is 50, so you have to get one.
Okay. Can I get the QR code? Because I do have to leave though.
Same
Okay,
time.
yeah.
Yeah, so it has to be 50, so like 50.
Go ahead and get your QR code to anyone that.
Yeah, that one, that.
But if y'all want to stick around, I'll go ahead and do number 49 because it's basically the same exact problem.
Oh, yes.
And we're gonna walk through it. Do you want me to let y'all try it?
Yes.
Okay, let's do that.
Okay, thank you guys. Bye.
Have a good one. Thank you for talking on Zoom.
Yeah, you're welcome.
Okay, so. Thanks. Okay, go ahead and try 49. Thank you.
I haven't done 49.
Pretty good. Finished? Wait, can you put it back in the back? Thank you very much. So remember, try to think of the steps that we went through in the previous one. You get stuck, raise your hand, Rich or I will go try to point you in the right direction, but we're not gonna tell you the path, because you need to remember how to do this yourself, okay?
Like, this is more of a path function than a state function. Like I said.
Good one, guys. Thank you for, nice seeing you. I'll have candy on Monday, I promise. Someone reminds me. Go, man. Wait, is there a Noah in here? Somebody wanted to interview me first.
I accidentally got spicy.
Yeah, it's all right. I like spicy. I like rich. I eat jalapenos for snacks.
I should do that sometimes, it's fun. Yeah.
I'm a fake.
I showed it spicy.
Oh, you can eat like, no, like soda spicy.
Oh, wait, soda?
Yeah.
So my hurts.
I did have half a ghost pepper once and I almost died.
I ate a habanero.
How did you go all the way to half? The first bite will be two.
Anyone,
Yeah, I
I
love.
got doing on this problem.
Oh,
Keep working. Keep working.
3 more seconds.
sorry. Wait, 3 more
There's
seconds.
a class in here at 4. No, here's lying. There's a class in here at 4, so I'll take my sweet time on this problem to explain it.
Okay, I got this wrong. We don't have to do all of this, right? 'Cause it's asking, like, water. Do you know
Why did you write water like that?
like, H1, that's how I read it's balance.
Okay, right.
You've never seen that?
No,
It's
I
really,
mean, I've seen it, but like,
it's easier to balance the equation if you write it like that. So I found the moles of weight. I found the moles of water.
Oh, the way Miss
I used, yeah, I know.
Yeah, she's doing
I used this to find mass. of water and cat, right? And I got my cube. So
temper mass water is slightly wrong.
it's 45.05. If you have that many moles, right, if you that times the T, that's more mass of water.
No, you can do it that way, but it's fast. But I have a funny-
Wanna tell me what you got?
100,
We assume like the density of this 112
5,
kilojoules per mole.
5,
You're very close to the answer I have,
right,
times 2.
and then.
No, the density.
You might, you got moles of water, right? So you did the mole to mole ratio, so you would have got like,
I see.
It's not exactly water, it's like.
it sounds like you did it right. You just might have forgot that one step. Because your answer is exactly twice my answer.
Use the water.
Yeah, because right times mole is H2O, not the precipitant, not the solid.
Yeah, so yeah, exactly. So it's asking for moles of kilojoules per mole of H2O.
Oh, shoot, this ain't right.
So I use density, so density is 1 gram per milliliter, you know, that is. This is grams.
Ani, was this a brain teaser?
You don't even want to know why I did that first. It was so stupid. I like found the mass of the reactants and then used that in the MCAT formula.
It's not that I'm running this.
It was like,
Yes.
really stupid. I don't know what I'm serious. It makes sense though. I don't know what I was thinking.
Um,
Okay, good.
somehow I got like the same amount of moles Yeah. No idea.
And then, okay, what modes do I use? Do I use the modes from the equation? Because, it's enthalpy is Q over moles. Do I use these modes?
Depends on what your limiting reagents is.
Well, what's the problem asking for, Maria? It says delta H. Find the delta H per mole of what?
I know, but I was trying to use the moles of water made from the reaction in the MCAT equation, but that's wrong. You have to use density, so I don't understand why we have to use density in one and the moles from the equation in the other. Yeah.
Because the moles of H2O being formed is not equal to the moles that was of like the solution. Or you just remember for the MCAT, you have to use the solution, the grams of solution.
Yeah, bro, but I don't know why I found.
You have the same limiting there.
Yeah, both of them the same thing.
That's what I thought.
Oh, that's right.
I think so.
But then how can you proceed it to both
Did
the
you get
same?
I mean, if the math checks out, the
Same
math checks out.
answer.
Wait, what did you get?
So that means you can use either or. the-
She got both of them as limiting reactants.
Both of them.
Yeah, I did too.
Oh, yeah, no limiting reactants.
So it's a perfect reaction.
I mean, not perfect, but.
Now, it's perfect if I do it, but if Rich does it, you get a 20%.
Theoretically,
They're
it could be
both the same
perfect.
amount of-
Theoretically,
Is
yes.
this what you guys are answering?
It doesn't, we just need, it doesn't matter which one you use.
Yeah, it doesn't matter which
They're
one.
about the same.
Oh, I thought I was using the one that got the same. Oh, no. Okay, thank you. Never mind. I can continue now.
But reading it again, I'm supposed to get.
Okay, now you.
5.8.
Okay. Is that what you got?
Yeah.
You got your money up,
What?
your money up.
Oh. I don't know what that means.
Does that make sense?
Don't worry about what it means. Don't worry.
Dylan, I have the answer, I think,
What do you get?
-55.8.
Oh, everyone is getting their money up today. Okay,
Reagents are flowing.
Negative?
it's negative, yeah.
Oh, y'all have the
Yeah,
answer.
it's-
I just.
Gosh.
You're fine.
Exactly.
Okay.
I don't pay attention to that.
Remember, slow and steady wins the race.
I'm been really negative. Hey.
What might be the
Wait, where is the negative?
The environment.
Coming from the.
Hated the environment, I could
You
print
do
it.
Negative, positive.
I'm gonna go ahead and get started on the problem. So if you haven't finished, I'm sorry, but you can finish as I go through it. Okay. So it's saying. Okay, so let's just read it out. When 25 milliliters of a 0.5 molar sulfuric acid is added to 25 milliliters of 1 molar potassium hydroxide in a coffee cup calorimeter at 23.5 degrees Celsius, the temperature rises to 30.17 degrees Celsius. Calculate delta H in kilojoules per mole of water, so that's important. Mole of water formed. And then you can assume that the volume is the sum of the volume. Wait, the total volume is the sum of each smaller volume, right? And then the density and specific heat capacity of the solution are the same as water, right? So we have this, we have that. And then it says the initial temperature and final temperature. Asking for delta H, which is equal to Q of reaction over moles. And in this case, it's moles of what? Water,
That's what it's. That's what it's breaking.
right? All right. So from there, we also know that we can just
Got lab
solve
this.
the mass of water, right? So it's 25 plus 25 because it's 25 milliliters.
Okay.
Plus 25 milliliters.
No, you're getting it.
50, and since the
Are you sorry? what?
density of water is 1 gram. Since the density of water, since the density of water is 1 gram per milliliter, 50 milliliters of that is equal to 150 grams. Alright. So first, we need to find the limiting reaction, and we use the molarity equations to find that, right? So if you do 0.025 liters
I would fall asleep. I'll be done with episodes.
times 0.5 molar, and I'm getting that from right here. It's equal to 0.0125 moles of H2SO4. All right,
So the equation was already balanced.
no, I forgot, I should have done that first, so. H2SO4 reacts with KOH. Or K2SO4 plus H2O. And to balance this, you need to put a 2 here and a 2 here. Okay. So we're looking for moles of water, so we're gonna go from 50, or yeah, so for every 1 mole of H2SO4. So when it's there are 2 moles of water. You all got that. This is all stuff that we learned in chapter 4, even before basics stoichiometry, right? So this will give me 0.025 moles of H2O. Right? Next thing, you do 0.025 liters. Assuming in chemistry, 0.025 moles of KOH. Yeah. Now we do for every 2 moles of KOH. We're going 2 moles of KOH, 2 moles of water are produced. Okay, so we're good on there. So now we can just multiply that out and you get 0.025 moles of H2O because it's 2 over 2. It doesn't do anything. There's no limiting reactant. Okay, so no limiting reactant, or you can say that both are the limiting reactant. They're both the same thing. So from here, we need to figure out the heat, right? Because we found the moles of water, but we need to find the heat of reaction, or the heat associated with the reaction. And we do that by using our negative Q of reaction, because we know that it's negative because the water's increasing in temperature is equal to Q of the water. Right? And from there we can solve for Q of reaction by multiplying by -1. So we're going to multiply by -1 on both sides, just so that way we're solving directly for Q of reaction. So you get Q reaction equals -Q H2O, right? Get that part. So from there, we can say, just rewrite this one more time, equals -Q H2O, which is equal to -MC delta T of the water, right? So therefore, we can say that Q of reaction is equal to this, because this is essentially this, just expanded, right? So if we plug in everything we have, we're going to get Q reaction equals negative, the mass of the water we said was 50 grams because we used the density. So 50 grams times the specific heat, which is 4.184, times the delta T, which is final, which is 30.17 minus initial, which is 23.5, and you should get 6.67 degrees Celsius. And this is equal to negative 1,395.364 joules Q reaction. Okay. From there, we just convert it to kilojoules, so we get negative 1.395. I'm just going to round that to 4 kilojoules. Cutting it close there. Okay. So now we have everything we need. Delta H is equal to Q of reaction. We found that. And we have moles of H2O. So all we have to do is plug those 2 variables in. So delta H equal to negative 1.3954 over what is it? I'm gonna actually just use, I know I rounded it here, but I'm just going to use the rest of the decimal places here so we can make sure we get the same answer. So 395,364 kilojoules over the 0.0 0.25 moles of H2O. And you should get delta H is equal to negative 55.8 kilojoules per mole. That's your answer. So again, if you still don't understand how to do these problems, you need to do more practice, and that's all I can say. I can't, I mean, I could do as many problems with you as possible, but at the end of the day, you need to work on these yourself, so that way you can, I mean, it's good to try to follow the process that I'm doing when you do it, but you need to actually solve these by yourselves. That way you know how to do it on the exam, because I'm not going to be able to guide you on the exam. Okay? So we definitely went over like 30 minutes than intended, but that's okay. I do need to go get a haircut right now, so I will have to say goodbye, unfortunately.
And he will see you with a fresh cut.
All right, have a good one. Thank you all for coming. You haven't. Everyone already signed. Or we're gonna get like 4. You stop recording.